Hi, this is Nasa Sareen, and you're watching me on 23rd September 2025. Welcome to NASA's Romance with Chemistry. Keep aside the heart, let's romance with the mind. And today's topic, which I have chosen, is molecular orbital theory. This molecular orbital theory is given by F. Hunt and R.S. Mulliken. Now, why did molecular orbital theory come into existence, and what was the theory before that? Of course, the theory before that is known as valence bond theory. Now, when a covalent bond is formed, when a covalent bond is formed, the two half-filled orbitals overlap. The two half-filled orbitals, the valence electrons, of course, overlap in the bond formation to form an atomic orbital, which was a fantastic theory called as valence bond theory. But then there were few failures in the valence bond theory. There were some drawbacks which led to the formation of molecular orbital theory. So before proceeding exactly what is molecular orbital theory, it's better we understand the drawbacks of VBT. So coming on to the drawbacks of VBT. Drawbacks of VBT. There are few of the drawbacks of VBT wherein the VBT couldn't explain why oxygen molecule is blue in color in liquid form. That is, it couldn't explain the colored nature of the molecules. So the first drawback is it couldn't explain, it failed to explain the colored nature of molecules. So what was the colored nature of molecules? That is, it couldn't explain why oxygen is blue in color when it is in liquid form. Of course, it couldn't explain that. Further, the VBT couldn't explain why and how the odd electrons enter into bond formation. That is, it couldn't explain how and why the odd electrons enter into the bond formation. Further, very important, the bond order is always not a whole number or integer. It is fractional also. So valence bond theory couldn't explain the fractional bond order. For example, if you are taking benzene, it is 1.5. How on earth can the bond order be fractional? So it couldn't explain the fractional bond order. For example, benzene, which is 1.5. And very important, that is the magnetic nature of a compound or the magnetic nature of a molecule. Suppose if I am going to take oxygen, oxygen has O2, which is 16 electrons, and these 16 electrons are paramagnetic in nature in reality, but according to VBT it is diamagnetic. So VBT failed to explain the paramagnetic nature of electrons. It failed to explain the paramagnetic nature of the 16 electrons of oxygen or the oxygen molecule. According to VBT, oxygen is diamagnetic, but in reality, oxygen is paramagnetic. So, VBT failed to explain the paramagnetic nature of oxygen. So, under the drawbacks of the VBT, we see that it couldn't explain the colored nature of molecules, wherein oxygen is blue in color in liquid form. It couldn't explain how odd electrons enter into the bond formation. Further, it couldn't explain the fractional bond order that which we see in most of the molecules. I have taken the example of benzene, which is 1.5, and very importantly, it couldn't explain the paramagnetic nature of oxygen. Now, because of all this, the VBT was nullified and the molecular orbital theory came into existence. Now, if we are considering the major part, that is the paramagnetic nature of the oxygen, let us discuss the magnetic nature. The magnetic nature of molecules. Now, according to VBT, it said that there are two types of the magnetic nature. Of course, there are ferromagnetism and all that, but he considered as paramagnetism and diamagnetism. Paramagnetism and diamagnetism. अगर लड़की सिंगल है तो प्यारी है, अगर लड़की कपल्ड है तो डायन है. Just joking. However, so if there are couple diene and single teri, that means if there is odd pair of electrons, then it is paramagnetic, and if it is even pair of electrons, then it is diamagnetic. Now, what is even? All those 2, 4, 6, 8, that is even. So, even pair of electrons should be diamagnetic, and 1, 3, 7, 9 are paramagnetic in nature. But care should be taken that the 10, okay, and the, of course, 10 and 16 are paramagnetic in nature. 16 is for oxygen, and oxygen is, it should be even. So it has to be diamagnetic. But we know experimentally, the boron and the oxygen molecule, that those are paramagnetic in nature. So how exactly 10 and 16 are paramagnetic? However, what is paramagnetic? Paramagnetism is where the electrons get attracted in the magnetic field. So attraction takes place here. Okay, they get attracted to the magnetic lines. The magnetic lines of the molecule get attracted in the magnetic field is known as paramagnetic, and when they are repelled, the magnetic lines, when they are repelled, then in the magnetic field, then they are known as diamagnetic. So VBT said that if there is odd pair of electrons, then it is paramagnetic. If it is even pair of electrons, then it is diamagnetic. Of course, odd is 1, 3, 7, 9, even is 2, 4, 6, 8 electrons. However, the paramagnetism deals with wherein the magnetic lines get attracted in the magnetic field, paramagnetism. When the magnetic lines of the molecule get repelled in the magnetic field is known as diamagnetism. But experimentally, it was seen that those which have 10 and 16, they are paramagnetic. How exactly a paired electron can be paramagnetic? That was the failure of VBT that gave rise to MOT, that is molecular orbital theory. Of course. So what is molecular orbital theory? When two atomic orbitals combine together to form a molecular orbital, then it is known as molecular orbital theory. Two atomic orbitals combine together. So what's happening here is there is an atomic orbital which combines with another atomic orbital, and it forms a molecular orbital which further forms molecules. This is known as molecular orbital theory. But is it how it is being formed? No, this is not the way it is being formed. So it actually takes place when an atomic orbital combines with another atomic orbital, and it forms a molecular orbital and molecular orbital. That means this is parent atomic orbital. When two parent atomic orbitals combine, they form two molecular orbitals. That means the number of atomic orbitals involved is equal to the number of molecular orbitals formed. Number of atomic orbitals involved is always equal to the number of molecular orbitals formed. But here I have not written like this. I have written one molecular orbital below and the other molecular orbital up. That is because of the energy level. Okay, so there is lower energy or lesser energy, and here it is higher energy. Now, what does it mean? It means that they follow the principle of both Pauling's and Hund's rule of maximum multiplicity. They follow all the three principles when they add the electrons into the atomic orbitals. That means the lower energy is going to take the electrons first, or the electrons are filled at the lower energy and then they are filled in the higher energy according to Aufbau principle. Now, which is the lower energy? That is the molecular orbital which is at the bottom is known as lower energy. Now, why is this molecular orbital at lower energy and why is this molecular orbital at higher energy? That is because of the constructive interference and the destructive interference. Then what happens here is whenever we know that electron is a particle or a wave. Okay. Here, because the weight of the electron is negligible, we are considering the wave characteristic of the electron. So, electron behaves as wave. If this is clear, okay. Now, when it behaves as wave, of course, when it is going to form the bond, whenever it is going to form the bond, it is an exothermic process. It is an exothermic process. Here, what happens is during the bond formation, it is constructive interference. What is constructive interference? Of course, you know this is a wave. You know this is a wave. So, one more orbital with the same wave nature. If this is there, what you get, the atomic orbital which you are getting here is because of the constructive interference. If the wave is in this way, where this is the crust and the another wave is from the trough, then this is known as destructive interference. So whenever the atomic orbital which is taking place in this form, it is known as constructive interference, and whenever you see in the other way, it is known as destructive interference. Now, whenever there is a constructive interference, there will be bond formation, and this bond is actually shown with lesser energy. What that means, it is more stable. Anything. Suppose if you are holding your hand like this for a long time in the higher state, you are not stable. But when you leave your hand light, okay, suppose you are sleeping, you just leave your hand on the bed. So that is stable. So anything at ground state is stable, okay. And here what happens? Attraction takes place. So here attraction takes place, and because of this there is lesser energy, and because of this it is stable. So in the constructive interference, what is happening is the nucleus, the electrons are between the nucleus, and there is attraction. Of course, when there is attraction, the energy becomes less. When there is energy less, then it becomes stable, leads to constructive interference wherein the bond is formed. If it is the other way around, then it is known as destructive interference, wherein repulsion takes place. Of course, the energy is high and it leads to unstable or non-stability. Now, if this is clear, suppose अगर आप लहरें देख रहे हैं, पानी में लहरें देख रहे हैं, the waves are moving, okay, and you listen to the melody. If it is a constructive interference, then you listen to the melody. Sometimes there will be पूरा सन्नाटा रहता है and you don't get to listen the waves, okay. इतना सन्नाटा रहता है, that means there is तूफान आने की कतार में है. So if you are having two friends, they are meeting after a long time, and suddenly they bump into each other, they want to talk to each other, and they're so happy, they come with so much energy, there is an attraction between them, there is a good dialogue between them, there is constructive interference. Because of this constructive interference, there is a melody in their relationship, okay, there is sound, there is beauty. But if two friends are coming, okay, they're coming with different frequency. One is coming with a lovable frequency and the other one is coming with a discomfort or hatred तो नहीं करेंगे, something, a different frequency, there will be destructive interference. दोनों में बातचीत नहीं होगी, दोनों में खामोशी रहेगी, and that will lead to in future noise. So sound is constructive and noise is destructive. The same thing is happening here. Anything that is happening here is known as constructive interference, and anything which is happening here is known as destructive interference. Whenever there is constructive interference, then it is stable, lesser energy. Whenever there is destructive interference, it is unstable and it is higher energy. And very importantly, you should know that, of course, the p orbitals and s orbitals come into the picture. So obviously there is sigma and pi that is coming into the picture. So whenever there is a molecular orbital at the below, then it will be sigma and pi. Whenever the molecular orbital is above, then it is sigma star and pi star. So now there are two types of orbitals which are formed, and let's name these orbitals. The orbital which is below is known as bonding molecular orbital or BMO. The molecular orbital which is above is known as anti-bonding molecular orbital, which is otherwise known as ABMO. If this is clear, so let's have a quick recap. So molecular orbital theory was given by F. Hunz and R.S. Mulliken, and in this, two atomic orbitals combine to form a molecular orbital, which in turn forms a molecule. Now, in this, the atomic orbitals combine. This is the parent atomic orbital. They combine together to form molecular orbitals. Number of atomic orbitals involved is equal to number of molecular orbitals formed. So, the molecular orbital which is at the below has lesser energy than the parent atomic orbital, and the molecular orbital above has more energy than the parent atomic orbital. Of course, the one which has lesser energy undergoes constructor interference, and it is stable, and it is because of the attraction, and the one which is above is due to destructive interference, and there is repulsion, and it is highly unstable. The stable one is known as bonding molecular orbital, which is indicated by sigma and pi, whereas the unstable one is indicated by sigma star and pi star, and it is known as anti-bonding molecular orbital. So if this is clear, then let's sum up very fast the postulates of molecular orbital theory. Anyhow, we have discussed all this. However, I'm just summing up all this. So the first postulates of molecular orbital theory is two atomic orbitals combine together to form a molecular orbital, which in turn forms the molecules. Now, suppose if I'm going to take H2, and if I'm going to take He. Helium is an atom and hydrogen is a molecule. So helium atomic orbital 1s2, whereas hydrogen it is 1s1, 1s1. So here what is happening? This is formation of atomic orbital, whereas here there is formation of molecular orbital which is taking place. So this is a molecule and this is an atom. The second point was whenever atomic orbitals are formed, molecular orbitals are formed, they are formed with proper energy and proper symmetry. That means 1s orbital always combines with 1s orbital. Same symmetry, same energy. 2s orbital combines with 2s orbital. There is no possibility of 1s combining with 2s. It's impossible. Similarly, px combines with px and py combines with py. Okay, suppose it is 2px combines with 2px and 2py combines with 2py. It is like this. There is no possibility of 2px combining with 2py. This is not possible. Just because monkeys look like humans, you cannot marry them, right? Monkey marries with monkey, humans marry with humans. However, sometimes humans behave like monkeys. You can't do anything for that. Jokes apart. So, of course, what I'm trying to say is the molecular orbitals always combine with similar energy and they combine with similar symmetry. Then that is the second postulate. The third postulate is atomic orbitals are monocentric, whereas the molecular orbitals are polycentric in nature. Atomic orbitals is monocentric, whereas the molecular orbitals are polycentric in nature. That means in atomic orbitals, the electron is ruled by one nucleus. Okay, in molecular orbitals, the electrons are ruled by two nucleus. कैसा हो अगर एक ही घर में दो मदर इन लॉस हो जाए? That is molecular orbital. Sad. होता नहीं है. However, so the molecular orbital is polycentric in nature, whereas atomic orbital is monocentric in nature. Further, the fourth postulate is number of atomic orbitals is always equal to number of atomic orbitals involved are always equal to number of molecular orbitals formed. And the last postulate is whenever the molecular orbitals are formed, they are formed according to Aufbau principle. That means they follow N plus L rule. That means the lower energy is being first filled, that is bonding molecular orbital is filled, then the antibonding molecular orbital is filled. The second is it follows the Pauling's exclusive principle, that is all the four N, L, M, S, okay, they are not same. They are not same. And the last one, of course, it follows Hund's rule of maximum multiplicity. That is, pairing is not possible unless and until each orbital has one electron. Suppose you have an orbital which has pi x and pi y. Okay, pairing is not possible unless one electron goes to pi x, then next electron goes to pi y, then the other electrons. So it follows all the three rules. Now, summing up, postulates of molecular orbital theory, of course, atomic orbitals combine to form molecular orbitals, wherein hydrogen it is a molecule and helium is an atom. So, whenever atomic orbitals combine, they always combine with proper symmetry and proper energy. Oneness combines with oneness and oneness never combines with 2x. Similarly, 2px combines with 2px and never the vice versa. Atomic orbitals are monocentric in nature, molecular orbitals are polycentric in nature. Number of atomic orbitals involved is always equal to number of molecular orbitals formed. They follow the Aufbau's principle, following N plus L rule. Lower energy is being filled first. So bonding molecular orbital is filled first and then antibonding molecular orbital. They follow the Pauling's exclusive principle and Hund's rule of maximum multiplicity. So this was a quick theory on molecular orbital theory. Now, moving on to what exactly or what kind of questions you're going to get in the competitive exam with regards to this topic. Now, the questions which you're going to get is really beautiful. I mean, you get many questions from here. Different types of questions, if I can list, then the first one will be the electronic configuration of a particular molecular orbital theory. So, electronic configuration of molecules based on MOT. They're going to ask the electronic configuration. We will come to that later. Now, the second question is the last electron or the incoming electron enters into which orbital? The incoming electrons enters into which orbital? They further ask the magnetic momentum, whether it is paramagnetic or whether it is diamagnetic. They ask the magnetic nature of a molecule, whether it is paramagnetic or diamagnetic. Most important, always ask the bond order. 2, 3, 4 molecules will be given to you, and with charges, without charges, neutral molecule, it will be given. They may ask you like O2, O2 plus, O2 minus, something like that, or O2, 2 minus, O2, 2 plus. Okay, they may ask their bond order. So, increasing order of the bond order, or they may ask you the bond length order. The bond order or the bond length order. They may ask you minimum bond strength. Minimum bond strength. Or they may ask you maximum bond energy. Maximum bond energy or amongst the given molecules. Or they may ask you which is most stable amongst the molecules which is given, or they may ask you which is least stable among the molecules. So different kinds of questions can be formed. Further, if you want to extend it, to coordination compounds or to the periodic properties, of course they may ask something like what is the value of the spin magnetic momentum? That can be one of the questions. Or they may ask you what is the value of N? N is nothing but the number of unpaired electrons. Or they may ask you the whether the molecule is colored or colorless. the molecule or ion which is being given is colored or colorless. If they want to extend further, there might be questions on the relationship of bond order, which is directly proportional to bond strength, which is directly proportional to bond dissociation energy. They are all friends, which is inversely proportional to bond length. Okay, if you know this order, then you can answer any questions related to bond order, bond dissociation energy, bond strength, and bond length. If they want, they can again relate this to lattice energy, of course. So all this is directly proportional to lattice energy. Now, lattice energy is directly proportional to electronegativity of side atom, and it is inversely proportional to electronegativity of central atom. Okay, so these are the different questions. If I am going to number them, that is 13, 14. So you can see almost 14 types of questions will come from this chapter in the competitive exam. So what are those? They can ask you electronic configuration of molecules based on molecular orbital theory. The last electron is entering into which orbital in this electronic configuration? What is the magnetic nature of the molecule, whether it is paramagnetic or diamagnetic? What is the bond order of the given molecules? What is the bond length order? What is the minimum bond strength or the maximum bond energy? The most stable molecule or the least stable molecule? The value of mu, this comes in coordination compounds, these three. Of course, this comes in chemical bonding of MOT. These three comes in coordination compounds. What is the value of the spin magnetic moment? The value of N, okay, number of unpaired electrons, and the colored or colorless molecule or ion. This comes in periodic properties, where the bond order is directly proportional to bond strength and bond dissociation energy, which is inversely proportional to bond length, which is directly proportional to lattice energy. Of course, lattice energy is directly proportional to electronegativity of side atom, which is inversely proportional to electronegativity of the central atom. So these are the different types of questions which will be asked, and we can pick few of the questions and solve them. But before proceeding with that, there is few things which we should know. So in this, we should know how to write a molecular orbital if it is, or how to find the bond order. Bond order below 14 electrons, bond order above 14 electrons, or bond order above 20 electrons. What is the formula? And is there a trick to remember the bond orders? Because if you know the bond order, then you know bond strength, bond dissociation energy, bond length, everything. It becomes very easy. So that, and how exactly molecular orbital theory proceeds. So first we will have little theory of it, and then we will go for direct questions. So starting on with the molecular orbital theory for energy of orbitals, when total number of electrons in a molecule is less than 14, and energy orbital when total number of electrons in a molecule is greater than or equal to 14. Here we have to remember that there is a small trick. If it is greater than or equal to 14, and if it is less than or equal to 14, that means we know 14 is nitrogen, so we can take the reference as N2, and we know more than 14 oxygen, of course, we are going to consider, and we take it as O2. And here you will have to remember that there is bumping triangle and there is following triangle. So this is following triangle. Okay, one triangle is following the other triangle, and this is the bumping triangle. One triangle is bumping into the other triangle. So if you find it very difficult to remember, you just remember the heart. Oxygen is nothing but heart. So if I am going to take the heart, of course, it is 1, 2. Okay, 1, 2. And if I am going to take another heart, 1, 2, 2, 1. Okay, 1, 2, 2, 1. So you can understand. heart. So 1, 2, 2, 1. If you can remember that, of course, the heart is not so pretty, however, but my heart is good. Okay, don't go with the diagram. So if it is 1, 2, 2, 1, okay, that is 1, 2, 2, 1 pattern, then it is oxygen. And if it is 1, 2, 1, 2 pattern, 1, 2, 1, 2, or if it's better we go from down, 1, 2, 2, 1, and it is 2, 1, 2, 2, 2, 1, 2, 1 pattern. Okay, 2, 1, 2, 1 pattern, then it is nitrogen. So we always go from lower energy to higher energy. So let us go this way. Okay. So if it is 1, 2, 2, 1 pattern, then it is oxygen. And if it is 2, 1, 2, 1 pattern, then it is for nitrogen. So all molecules which are less than 14 and all molecules which are more than 14. Now if I am going to take molecular orbital for the nitrogen molecule, suppose it is for nitrogen molecule. So of course it has like 1s orbital. So it has 1s orbital. So this is the parent orbital and it is going to form the molecular orbital. This is 1s, 1s. So that is the orbital. Of course, we are moving from lesser energy to the higher energy. Okay. This is 1s orbital and the 2s orbital, 2s. The 2s orbital. Of course, we have seen that similar orbitals with same energy will combine together to form molecular orbitals. This is 2s orbital and we have to go with 2-1-2-1 pattern. So let us draw this. We have 2px, 2py and 2pz. Okay. So to that, okay. So I said it is 2, 1, 2, 1 pattern. 2-1-2-1 pattern. So totally how many electrons do we have? We have 14 electrons. Let us start filling these 14 electrons. So in the 1s orbital, 1, 2, 3, 4, 5, 6, 7, 8. Okay. Here 9, 10, 11, 12. It is 9, 10, 11, 12. Okay. 13, 14, 15 and 16. 15 and 16. Because this is a nitrogen molecule, we are going to stop here. So it is 14 electrons. Now, what you can see here is the last, it is being paired. Okay. So nitrogen with 14 electrons is paired. If we are going to consider the same thing, of course, I'm not going to write for oxygen. Okay. For oxygen molecule, this will be same. This one will be same. That is 1s and 2s orbital will be same. The 2p x, 2py and 2pz orbital will be different. That is, we are going to change the pattern. Suppose you get something like this. Okay. Which pattern we are going to follow? We are going to follow 1, 2, 2, 1 pattern. So 1, 2, 2, 1. Okay. So similarly, as you see here, 2, 4. We have oxygen as 16 electrons. We have 2, 4, 6, 8. Till 8 it is done. Now 9, 10, 11, 12, 13, 14, 15, 16. You can see there is unpaired electrons. Okay, you can see there is unpaired electrons. Because of unpaired electrons, this deals with paramagnetic nature of the oxygen molecule. Now, instead of writing this completely, you can just write like 1s orbital, 2s orbital, And this is 1s, of course, bonding, antibonding. So can I say it as Na, Nb, bonding, antibonding, bonding, antibonding. Okay, this is with regards to 1s and 2s orbitals. Then coming on to the other one, bonding, you have 2, okay, and 2 1 2 1 pattern. Now this here, this is NB and this is Na. Now if you are going to add, this is for nitrogen molecule, 2 4 6 8 9 10 11 9 10 11 12 13 14. This is clear. Now there is a formula for bond order which is nothing but Nb minus Na. Bond order is equal to Nb minus Na by 2. How many Nb is there? 2, 4 and 6, 8, 10. So that is equal to 10 Nb minus Na is 2, 4. That is 4 divided by 2. 10 minus 4 is 6 divided by 2. That will be 3. So nitrogen will be having bond order equals to 3. So the bonds for nitrogen will be 3 bonds. Similarly, for oxygen, if you are writing, we can write this is same. Okay, 1s, 1s, 2s, 2s. So this is Nb, Na, Nb, Na. Till here it is same. Let us follow this pattern, that is 1, 2, 2, 1 pattern. This is Nb and this is Na. Now let us fill the 16 electrons. 2, 4, 6, 8, 9, 8, 10, 11, 12, 13, 14, 15, 16. Okay, same formula. Bond order is equal to Nb minus Na by 2. So Nb is 2, 4 and 6, 8, 10. That is equal to 10. And this is 2, 4 and 6 divided by 2. That is 4 divided by 2. That is equal to 2. So oxygen molecule has bond order which is equal to 2. If this is clear, how to name these orbitals? As I said, this will become, this is sigma, this is sigma star, or sigma 1s, sigma star 1s. This is sigma 2s and sigma star 2s. If this is understood, always whenever there are two orbitals, it is pi x and pi y, and whenever there is one orbital, then it will be sigma. Okay, so z is always sigma, x and y is always pi, if this is known. So this will be pi x and pi y. This will be sigma z. Pi x, pi y and sigma z. This will be, however, we have not filled, but this will be pi star x, pi star y and sigma star z. Coming on to this, this one single, so it is sigma 2pz, sigma 2pz, and this will be pi 2px, pi 2py. Okay, and this will be pi 2px. It is pi star because it is antibonding. So pi star 2p1. So let us learn to write the electronic configuration for molecular orbitals. So I'll just erase this so that we learn to write electronic configuration for both. Now, for the nitrogen molecule, the electronic configuration will be, okay, sigma 1s, okay, is less than sigma star 1s, which is less than sigma 2s, which is less than sigma star 2s, which is less than 2p, 2 pi 2px, pi 2px, which is equal to, they are on the same symmetry. That's why, which is equal to pi 2py, which is less than pi, sorry, sigma 2pz. This is clear. Now let us fill the electrons. How exactly we fill the electrons? 2, 4, 6, 8. Okay. 9, 10, 11, 12. That's how you fill. And 13, 14. So of course I'm changing this. Okay. So it is 14 electrons. So where is the last electron entering into the nitrogen molecule? Then you should say it is entering into the sigma 2pz. Okay. If he is going to ask, they will twist, they won't ask this kind of direct questions. They will ask you where will be the new electron entering into the N2 plus molecule. N2 plus, that means one electron is less. Or they may say N2 2 plus. 2 plus means 2 electrons are less. So of course this complete will go off. Okay, the last electron will be in pi 2py. So you should know which molecule is being asked and how to proceed with that. Similarly, if I am going to write with respect to oxygen, the electronic configuration with respect to oxygen, then I will be writing as, this will be same. Till here it will be same, of course. So till here it is same. That is sigma 1 square, sigma star 1 square, less than sigma 2 square, less than sigma star 2 square, which is here, which is less than sigma 2pz, which is less than, but these two are in same symmetry, same energy, not symmetry, same energy. That is the pi 2px, which is equal to pi 2py, which is less than pi star 2px, which is less than pi star 2py. So where is the last electron entering into the oxygen molecule? That is 2, 4, 6, 8, 10, 11, 12, 13, 14, okay, 15 and 16. These are in same symmetry. So 1 enters here, okay, and 1 enters here. So 1 electron is entering into the pi star 2py. That is the entering of the electrons in oxygen molecule, that is O2. What if it is O2 plus, O2 plus or O2 2 plus? If it is O2 plus, then 1 electron will be entering into pi star 2px. But if it is O2 2 plus, that means the last electron is entering into pi 2px, sorry, pi 2py. So if it is O2 molecule, then the last electron is entering into the antibonding molecular orbital. If it is O2 plus, then also antibonding molecular orbital. But if it is O2 2 plus, then the last electron is entering into the bonding molecular orbital. So twist and turn will be asked, any question can be asked, and you should know how to proceed with it. So if this molecular orbital is being understood, then let us proceed with some other simple questions which are related to the bond order, They may ask any molecules bond order, any molecules. They may ask you like He2 plus, lithium 2, nitrogen 2, N2 plus, N2 2 minus, N2 2 plus, O2, O2 minus, O2 2 minus, O2 plus, O2 2 plus. Anything can be asked. That means they can ask you oxygen. They can ask you O2 plus, O2 2 plus. They can ask you O2 minus, O2 2 minus. Possible. They can ask you N2, N2 plus, N2 2 plus, N2 minus, N2 2 minus. They can ask you either this series and they ask you what is the bond order, give the bond strength, give the bond length, or they can ask you these questions, or they can ask you with regards to oxygen versus nitrogen also. They can ask O2 versus N2, N2 plus. Anything can be asked. So how to calculate? It is very simple. Oxygen is 16. So this is 16. Nitrogen is 14. Okay. Plus means you're going to add the electron. Minus means you're going to really? Okay. Minus means you are adding the electron and plus means you're going to remove the electron. So if it is 2 minus, that means 2 electrons is being added. That is, this becomes 18. Sorry, this is single electron, so 17. This is 18. Similarly, N2 minus will be 15. N2 minus will be 16. If it is plus 1 electron is being removed, that is 15. 2 plus is 14. Similarly, nitrogen is 14. 1 electron is being removed. That means it becomes 13 and this becomes 12. Okay. So this is how you're going to calculate the number of electrons. Okay. Now, how to know the bond order and how to know the order of bond order? That is very easy. So I have just given you this many and many can be questioned. So how to know the bond order? For that, there is a simple way. You can either go with this format or you can go with this format depending on what is being asked. So this is a trick to know the bond order. So if it is less than 8, you're going to go with this. So 1 to 8, you're going to go with this. If it is 8 to 14, then you're going to go with this. Or suppose 8 to 20. Okay. If it is, so this trick is exclusively to find bond order which is less than 20. So less than 20 electrons. This is the trick to find the bond order. More than 20, we have a different trick. So if it is less than 20, then you can remember like this. 0, this is 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, simple. How to remember? So this becomes, here you have 0.0, this is 0.5, this is 1. Okay, so very simple. 0, 1, 2, 3, 4, 5, 6, 7, 8. For 0 electrons, 4 electrons, 8 electrons, the bond order is 0. For those which have 1, 3, 5, 7 electrons, the bond order is 0.5. For those which have 2 and 6 electrons, then the bond order is 1. If that is clear, the next one is, this is 14, okay, 15, 16, 17, 18, 19, and this is 20. Similarly, so we have finished till 8, 9, 10, 11, 12, 13, and 14. So for 14, the bond order is 3.0. For 15, you're going to reduce 2.5, okay, 2, 3, 2.5, 2, 1.5, 1, 0.5, and 0. That is what we saw, right? 8 is 0. Let us start like this. So 8 and 20 is 0, 9 and 19 is 0.5, 10 and 18 is 1, 11 and 17 is 1.5, and so on. So this is for those bond orders which are less than 20 electrons, and this is how we are going to go with it. Suppose now I'm going to pick this molecule. Okay, either I'm going to pick this half, this half. So who has the highest bond order? So I have written, suppose, oxygen O2, and I'll take O2 2 plus, and from here I will take O2 minus. Between these three, okay, which has the bond order more and which has less. So O2, I know it is 16 electrons, and O2 2 plus, it is 14, and O2 2 minus is 18. So in that case, the 16 electrons will have bond order equal to 2.0. The 14 one will have 3.0 and the 18 one will have 1.0. So which has the highest bond order? The bond order for these three will be, the first one is 3, 2, 1. That is O2 2 plus is greater than O2, which is greater than O2 minus. This is the bond order. If they ask bond strength, same thing. If they ask bond energy, same thing. But if they ask bond length, we know that bond order is inversely proportional to bond length. That's why we are going to reverse this. We will say O2 minus is greater than O2 is greater than O2 2 plus. I suppose this clarity is done. If they ask most stable, you know which is most stable. If they ask least stable, you know which is least stable. So O2 2 plus is most stable and O2 minus is least stable, because whoever has the highest bond order is stable. But sometimes there will be tricky questions. Of course. So let's take one tricky question. Okay. Suppose if they are going to ask the bond order with regards to, or give the stability order of H2 minus and H2 plus. Difficult. So what is H2 minus? It is how many electrons? Minus means you have to add. So it is 3 electrons. And H2 plus means how many electrons? So it is 1 electron, right? Now, what's happening here is, suppose if I am going with molecular orbital theory or the molecular orbital, so I have 3 electrons for hydrogen. Okay, this is the bonding, oneness, bonding and anti-bonding. So this is NB and Na. This is for H2 minus. Okay, similarly, I have NB and Na for H2 plus. Fine. So this is oneness orbital. Okay. So sigma oneness, sigma star oneness. This is sigma oneness, sigma star oneness. So here there are 3 electrons. I am entering the 2 electrons here and 1 electron here. And here it is only 1 electron. So there is 1 electron here. Okay. So if that is done, we know that bond order is equal to Nb minus Na by 2. So how many electrons we have? That is 2 minus 1 by 2. That is 1 by 2. So the bond order is 0.5. What is the bond order? That is 0.5. And here in H2 plus, okay, we have only 1 electron. So in the it becomes bond order is equal to 1 minus 0 by 2, which is again half, which is nothing but 0.5. How will you say which is more stable? Tricky. H2 minus, H2 plus. 3 electrons, 1 electron. We tried with bond order formula and both are getting 0.5, but you have to choose one of the options. You have to either say H2 minus is greater than H2 plus, or you have to say H2 plus is greater than H2 minus. You cannot say both are equal. That option is not there. In that case, what do you do? Very, very important. Always we know that stability is always for bonding. So bonding orbital, molecular orbital is directly proportional to stability, and anti-bonding molecular orbital is inversely proportional to stability. So keeping this in mind, if you are going to see the Bonding molecular orbital. See here, the anti-bonding molecular orbital doesn't have electrons. So obviously, our answer will be H2 plus is greater than H2 minus. Isn't it easy? Because the anti-bonding molecular orbital doesn't have electron here. The electrons are filled in bonding molecular orbitals. So this is more stable. Here you can see one electron which is there in anti-bonding. So you nullify this. Okay. So this is causing instability. This electron is causing instability. So H2 plus is greater than H2 minus with regards to the stability of the molecule. If this is understood, then of course bond order questions will come for molecules more than, that is for molecules which have more than the 20 electrons. The molecules which are having more than 20 electrons, what is the bond order? If they are going to ask, there is a very simple formula for that. Bond order is equal to 1 plus number of pi bonds by number of sigma bonds. Very simple. Bond order is equal to 1 plus number of pi bonds by number of sigma bonds. Suppose if they are, of course, this doesn't hold good for benzene. I'm sorry. So for benzene, this formula doesn't hold good, but for others, this works. Okay. And of course, the other formula which I gave you, bond order is equal to Nb minus Na by 2. This also will hold good for molecules which have more than 20 electrons. So this is one of the formulas. This is one of the formulas. Okay. And the one more formula will be like bond order is equal to number of bonds between any two atoms in resonating structures or in all resonating structures by total number of resonating structures. So there is three formulas for those which have more than 20 electrons. One is bond order is equal to 1 plus pi by sigma. This doesn't hold good for benzene, and you should remember benzene has fractional bond order and it has 1.5 as bond order. Always asked, very famous question. The other one is bond order is equal to Nb minus Na by 2. The third one is bond order is equal to number of bonds between two atoms in all the resonating structures and by total number of resonating structures. Suppose there is a question. Find the bond order between CO2 and CO3 2 minus. Okay. Suppose this is first, second and third. If they are going to ask the question like this, you are not going to sit and try the other trick. Okay, because these are the molecules which have more than 20 electrons. We are going to choose the first formula, that is 1 plus pi by sigma. So we know CO can also be written as C triple bond O, and CO2 can be written as this, and CO3 2 minus can be written as, we know the Lewis dot structures. Okay. If this is done, now we know that bond order is equal to 1 plus pi by sigma. So it has 2 by 1. And here you have 1 plus 2 pi's and 2 sigma. And here you have 1 plus 1, 2, 3, 1 pi and 3 sigma. So the bond order here will be equal to 1 plus 2, that is 3. And here the bond order will be equal to 2 ones, so that becomes 2. And here the bond order will be equal to 1.3. So it's easy. Now you know the bond order, which is more. So 3, 2 and 1.3. So the answer will be 1 is greater than 2 is greater than 3, or CO is greater than CO2 is greater than CO3. 2 minus. So these kind of questions will also come wherein you are going to put the formula for more than 20 electrons. If this is understood, let us move to the last part of this. That is the magnetic momentum. Of course, I don't have to deal with this because this is an extension for coordination compounds. But however, the magnetic nature or magnetic behavior, mu is given by root of n into n plus 2, which is dm, which is known as Bohr's magnetism. So m is magnetic nature. M stands for magnetic momentum. N stands for magnetic momentum. N stands for number of electrons or unpaired electrons. Number of unpaired electrons. Dm stands for Bohr's magnetism, which is nothing but the unit of it. Now, if this is understood, there is a simple way of remembering. Depending on number of unpaired electrons, the spin magnetic moment can be calculated. If it is 1, 2, 3, 4, 5. If the number of unpaired electrons is 1, then mu will also be 1, 2, 3, 4, 5. How easy? How stupid? Because we are not adding fractions. So this becomes 1.73. This is 2.83. This is 8.78992. Isn't it easy? So if n is 1, mu is 1, but it is 1.73. 2, 2.83, 3, 3.87, 4, 4.89, 5, 5.92. Sometimes they give you the same magnetism in a different way. That is 3, root 8, root 15, root 24 and 35. So root 3, root 8, root 15, root 24 and root 35 is being given sometimes. So you will have to, based on this tableau column, you can actually calculate the number of unpaired electrons and you can calculate the Bohr's magnetism. Suppose if they have given, like for example, the mu, okay, if there is a question where they say the mu of a molecule is 15 dm. So find n, number of unpaired electrons. So if it is root 15, then number of unpaired electrons will be 3. N is equal to 3. If you know this, it's easy. Now, if n is equal to 3, okay, sometimes they ask you the paramagnetic nature of the molecules. Suppose it's like they can ask you for iron. Suppose they are asking you for iron. Iron is nothing but 26. Satai V chroman fico nipuja. Okay, so iron is 26. So if it is 26, 6 plus 2 is 8. Okay. Now, if it is Fe2 plus, it's very easy. So if how to calculate this? So if it is iron 26, which is nothing but argon 18, okay, and 4 is 3d. So 18, 19, 20, 26 is 3d6. Okay. So if it is 3d6, how you are going to fill the electrons? Okay. So n is equal to how much? Unpaired electron 4. What will be the Bohr's magnetism? That will be 4.89. Or what will be the Bohr's magnetism? Root 24. Easy. If they ask you instead of Fe26, if they ask you Fe2 plus, okay, if it is Fe2 plus, there is a shortcut. So we know iron is 26. So 2 plus 6 is equal to 8. 2 plus 6 is equal to 8. 8 minus 2. 2 electrons are there. Minus 2. If it is Fe3 plus, then minus 3. That simple it is. So 8 minus 2 is 6. So it is D6. Okay, Fe2 plus will be D6. If it is Fe3 plus, then it will be iron is 2 plus 6, that is equal to 8. 8 minus 3 will be 3. 8 minus 3 will be 5. So it will be 3d5. So Fe2 plus will be 3d6 and Fe3 plus will be 3d5. So if you are going to fill the electrons, so here n is equal to 4, and if you are going to fill the electrons here, then n is equal to 5. So number of unpaired electrons in Fe is 4. Number of unpaired electrons in Fe2 plus is also 4. But number of electrons, unpaired electrons in Fe3 plus is equal to 5. So in Fe2 plus, the Bohr's magneton is root 24 or 4.89. In Fe3 plus, it is 5.92 or root 35. So what you understand here is, like, the more number of unpaired electrons, the more is the magnetic nature. So n is directly proportional to mu. That is, number of unpaired electrons is directly proportional to spin magnetic moment. So, and further, this is also directly proportional to paramagnetism. Okay. The more number of unpaired electrons, more paramagnetic it is. Further, this is also directly proportional to metallic bonding. That means the one which has more unpaired electrons will have more metallic bonding. So they can ask you questions on calculate the Bohr's magneton for this particular ion or this particular atom. They can also ask you what is the paramagnetic nature of that. They can also ask you with relation to how exactly how strong is the bond, metallic bond. They can ask you number of unpaired electrons and what else? Of course, color. They can ask you color. There is a very easy trick for color, that is Sati-Cousin. Sati-Cousin. That is 1, 2, 3, 4. That is Sc3 plus, titanium 4 plus, Cu 1 plus, and Zn 2 plus. These are colorless. Except for these 4, all are colored. So many types of questions can be asked in molecular orbital theory. I suppose I have done justice with the topic and I have touched most of the questions, and it's 1 hour 7 minutes and it's too big lecture. Hope it helps. Done with most of the tricks, done with most tricky questions also. What you should do, what kind of questions will come, what kind of twist and turn is done within 1 hour as much as possible. The intricate details for molecular orbital theory is being given. Now NASA is signing off for today on 23rd September 2025 with molecular orbital theory. So next time we will deal with a new topic of inorganic chemistry. Thank you. See you. Hope it helps. Have a great day.